Well, hello everyone. This is essentially our replacement from our holiday on Monday. The section I'm going to deal with in this case is section 16.3, which is called the Fundamental Theorem of Line Integral. So basically what this is going to do is to show you a quick way of finding line integrals. So a typical line integral might be something like this. A line integral of C. I'm going to do it on a vector field, a vector function, xy, and dr. So we're looking at line integrals that have that basic format. Now, the difficulty that we got last week was that there's a lot of work involved in this, because essentially you have to find a parametric equation of this guy, right? An x equals function, a y equals a function of t, and then all the x's and y's get turned into t's. You start at whatever t a to t equals b, and then this fella here essentially became r dashed of t, right? So you have to differentiate x with respect to t and y with respect to t, and it was a big long integral, and it would be nice if there was a better, more efficient way of doing it. And this is essentially what we have here. It's going to take us through a number of steps before we actually get to calculate a line integral. So let me start with just the first step. If you have a vector function, a vector field, f, and I'm going to call its components, this is a 2D one, P and Q. If we have a 3D one, it'll be called P, Q, and R. And we're going to talk about a thing called a special subgroup of these vector functions, vector fields, and these are called conservative fields. These are the really good guys that you can use the shortcut on. If it's not a conservative field, you cannot use this shortcut, the fundamental theorem of line integrals, to do it. You have to do it by last week's method. And, you know, sometimes you can't help it. So what's the test for a vector field to be conservative? Well, the derivative of this, the first term, with respect to y, must equal the derivative of this guy with respect to x. So an example of that might be question 1. And here we have our guy, and he's going to be called xy plus y to the 4. And the second fella is going to be called x cubed plus 4xy. So in my naming, this is P and this is Q. So I'm going to find the partial derivative of P with respect to y. If you differentiate that with respect to y, you get x, and this guy, you get 3y cubed. And then we do the partial derivative of Q with respect to x. And if we do that, we get 3x squared plus 4y. And you can see that these two are not equal. So this one is not a conservative field. Now we're going to get a number of questions where that's all they ask you to find out. Is this vector function, this vector field, is it a conservative field or is it not? And your answer is going to be, no, it's not. Yes, it is. And then they add an extra little bit, which is this guy. If you do have a conservative field, right? So this is true. These are equal. If you do have it, then you can factor in this fella. And he says that for every conservative field f, right, in this format, there's going to exist a unique function called the potential function, right? This is not a vector function. This is a function of x and y. So it's going to be, you know, x cubed plus xy squared. And this unique function called the potential function, f of xy, has the property that the gradient of f of xy is the vector field. Now, since this function is not conservative, That's the end of the question, and you just put in DNE. So let me go and find a new one that does work, right? That is a conservative field, and then we can work on it. Well, it didn't take me long to find one. Here's an example. The vector function is y squared take away 6x, comma, 2xy. And this is going to be p, and this guy's q. So differentiate p with respect to y, and I get 2y, and I'll differentiate q with respect to x, and bingo, they are equal. So we can conclude that f is a conservative field. So what we're left with now is a bit trickier. We are now going to try and find. So essentially, this is what we're going to do. How do you find the potential function? Well, what we know is that the gradient of it is equal to this guy. So if I find the gradient of this function, we know it's the partial derivative of f with respect to x, comma, the partial derivative of y. That guy. And we know it's equal to this guy. So what we're trying to solve is, we're trying to find a function, little f, whose derivative with respect to x is this guy, and at the same time, its derivative with respect to y is equal to this guy. So if I write them down, it looks something like this. The partial derivative of f with respect to x is y squared take away 6x, and the partial derivative of f with respect to y is 2xy. And so you might be thinking, well, how are we going to get from knowing what the partial derivative with respect to x is of f to actually finding out what the function f is? Well, it's a bit like if someone tells me the derivative of something is this, then if I integrate this, that's who he is. So I'm going to integrate him, and I get that guy. And I'm going to integrate it with respect to x. So that guy is going to be y squared x, and that guy is going to be negative 3x squared. Now, normally what you would do when you integrate a function and there's no limits of integration, you'd put a plus c here. And I am going to put a plus here, but not plus c, because plus c implies that the answer is an unknown number. When you integrate something with respect to x, you're treating y as a constant. So what you have to do is imagine that this arbitrary constant is just a function of y. And this guy is really just a placeholder. He really doesn't matter that much, as you're going to see in a few moments. But it's there because it needs to be there. Now let's integrate this guy, right? This guy here, and integrate him with respect to y. Well, if I integrate him with respect to y, check I got this guy sorted out. Okay. Then what do I get? I get essentially y squared x plus an arbitrary constant, but this time since we're integrating with respect to y, our arbitrary constant is basically x's. So I'm going to call this h of x. Now, the last piece is the bit that gets people for a while. And I'm not adding these things, I'm just putting a little line to kind of emphasize something. Our function, f, has to be this guy and it has to be this guy. And these little extra bits at the end are the mechanics of why that's going to work. it has to have all these features. Now, when I look at it, they both share that guy, so I'm sure that's true. Now, you might say this guy only has a minus 3x squared, which I totally agree, it only has a minus 3x squared. But this guy here is a placeholder for it. In other words, if you've got anything with x's, you can use it. So I can now put those two together, and the arbitrary constants, these guys here, have done their job. This is the unique answer to our original function. Technically, you could say +1, +2, but we just pretend that doesn't matter, right? These are the key guys. We now have our function in its full format. There's the potential function. So let's try somebody else. Let's go for a trick one. So this is question 4, and our vector field, vector function, this guy, is y e to the x plus sine y, and e to the x plus x cosine y. This guy's going to be p, and this guy's going to be q. And you are going to trust me that if I differentiate this guy with respect to y, it's the derivative of this guy with respect to x. So you can check it. It is a conservative field. You really do need to test for that, because your answer could simply be it's not a conservative field, and that's the end of the question. So we now know by using this that the gradient of the potential function f, which is the partial derivative with respect to x and y of f, should equal this guy, y e to the x plus sine y, e to the x plus x cosine y. Well, that means that this fella has to equal the first guy. And this guy must be the second partial derivative. So let's see what we can get. I'm going to do it in red. Here's f. Let's ignore this fella for a minute. I'm going to integrate this expression, with respect to x. So that guy, oh, you get that. And this guy, you get an x sine y. And the arbitrary constant is some function, I'll call it g of y. Then I'll do this fella, but I'm going to integrate him with respect to y. So I get this guy. I'm going to integrate him with respect to y. Just pausing for a minute, you get that guy. And the arbitrary constant is some function in terms of x. Okay. Let's combine these guys. Both of them have a y e to the x. Check. Both of them have an x sine y. So in this case, that didn't really matter. But can you pretend for a minute that I had a plus x squared, then you'd have a plus x squared here. If it had this one had a minus y cubed, you'd put minus y cubed here. So you're merging the two or blending the two together to create one function that would work in both cases. And these two little placeholders take care of the math to make sure that it's allowed. So we have our potential function. And he is that guy. Okay, what we just did gets you as far as question 6. So now we're looking at the accumulation of all these pieces. We're going to get a function and it's going to be a conservative field. We'll either be told it's a conservative field or we'll assume that it is. But if it's asked for, we can check. We check by showing that this is equal to that. What we'll then do is find the potential function using the methods we did earlier. And then we come to the third and final part of the puzzle, which is really amazing. The fundamental theorem of line integrals says that if you have a line integral of this format, it can be calculated by just evaluating the potential function at the end of the journey, take away the potential function at the beginning. Right? So f of xy is your potential function, and a and b are the position vectors, I would call them coordinates, of the start and finish of the curve. And that is really not intuitive, because what it means is this. Can you imagine that we have a vector field with vectors doing their thing? And you start at this point here, right? Call it A. And you do a route, whatever route you feel like, and you finish up here at some point B, put its position vector, it's B, and you're traveling along it. As long as that vector field was a conservative one, you only need to evaluate it at this guy here. Let's pretend this guy is 1, 2, and this guy up here is 10, 12. You only need to evaluate the potential function at the coordinates at the end, take away the guy at the beginning. Now you might say, well, you know, if you do a different route, you would end up with a different answer. But no, the fundamental theorem of calculus says, no, that's not the case. As long as you start here and finish here, you can take any route you like. As long as it's a conservative field, you will end up when you're finished, although it's a totally different curve, right? That's a different curve from that one. You end up with the same answer. So that is pretty impressive. That guy is him. Which means a lot of the things that you had to do last week, find the parametric equation of the curve, find the start t, finish the end t, or replace all the x's and y's by variables in terms of t, and what else? And then put the whole package together with the dx and the dy being replaced by some function dt's. Put that whole package together, and then you get very often a really ugly integral that you then have to fight your way through to get an answer. And if you had a straight line going up, this picture's getting ridiculous, but if you had a straight line, you know, 2 straight lines, if you were doing it with last week's work, you'd have to find this line integral and then this one totally separately and then add them up. So this guy is pretty cool. So let's give you some practice, doing some examples of that. So question 7. We have a vector field, which is 2x and 8y in this case. And the curve C is following x equals y squared. And it's going to do it from the point 4, -2. So that's basically the start. And it's going to finish at 1, 1. That's the end. And if you wanted to draw what x equals y squared looks like, it basically looks like this guy. And we're going to start at some point called 4, -2, which I'm guesstimating is about here. And then we're traveling along the curve until we get to this point here, which is coordinates 1, 1. So there's your curve C. Now, technically, we have to go through the whole set. So I'm going to, this time, I'm going to prove it's conservative field. In a lot of the other questions, to save time, I'm going to say, yeah, it is. You go and check it yourself. So according to my naming system, that's P and that's Q. So the partial derivative of P with respect to Y is 0. And the partial derivative of Q with respect to X is 0. Yep, they're equal. The fact they're equal to 0 isn't significant. All that we care is that they are equal to something, and they are. So now we're going to move on to finding the potential function, because we know that is true. And this fella is equal to that, and this fella is equal to that. And so we have the partial derivative with x is 2x. When you integrate it, you get x squared, and the arbitrary function is some unknown constant in terms of y. And then you do the second guy. And this fella, when you integrate it, I believe gets you 4y squared plus some arbitrary constant, which we consider to be a function of x. And so when you combine them, you get an x squared and a 4y squared. And when we merge them, this guy and this guy merges, and these guys are the placeholders that allow that. So we now have our potential function is equal to this guy. And now to complete the process, let's find the line integral of this guy. Well, he is equal to the value of the potential function at the end, take away the value of the potential function at the start. Okay, so this is the end position, and this is the start position. Well, if you evaluate this guy at 1, 1, you get 1 squared plus 4 lots of 1 squared. Take away, if you evaluate this function at what, 4, negative 2, you get 4 squared plus 4 times negative 2 squared. And this guy is 1 plus 4, which is 5. And this is 16, so is that 16? So we'll take away 32. And that gets me negative 27. And we are finished. Cool. Line integrals can be 0, they can be positive, they can be negative. They're basically calculating the work done in traveling through this vector field using this curve. So like imagine there's a vector field here, like wind blowing. And sometimes you get negative answers because you actually get energy, gain energy, rather than lose it. Now, what do you think would have happened if the only change I had made to this question is that you started at this point and you finished at that point? So you basically just go down the curve instead of up the curve. Well, if you look at the way the thing's evaluated, it's pretty easy to know what's going to happen, but this is the long way of finding out. The value of the function at the destination, the end. Take away the value of the potential function at the start. Now we already know what these guys are equal to. This guy is 32. Take away this guy is 5. And so the answer is 27. And I don't think that's too surprising. You know, it's a bit like if you climb uphill, you get one answer. And if you climb downhill, you get a total negative result, numerically the same, but the sign-wise is different. And that's also true. So be careful when you're doing some of these questions in case you get your start and finish coordinates mixed up, because you might have thought it was 27, when in fact, in the correct direction, it's negative 27. Are we good? I hope we are. Let's move on. So, what other one should we try? It's pretty straightforward. Right. This question superficially looks different from the previous one, but and question 8 when you do it as well, but it's not really. So let's show you how you tackle it. So here is our vector field. It's given as 1 plus xy in brackets, yikes, e to the xy, a lot going on here, comma, x squared e to the xy. No, okay. And can we just assume that I've checked it and it is conservative? So that means we can now find the potential function using that property. So this guy is equal to 1 plus xy e to the xy, comma, x squared e to the xy. Well, if I match the first one up, and while I'm at it, I'll multiply it through. We get that guy. Now, to integrate this guy is going to take a bit of work. You integrate this guy with respect to x, you will get e to the xy, and then that y gets you a 1 over y. A bit like e to the 2x would get you 1/2 e to the 2x. Now, if you're going to integrate this guy, you are going to have to, in fact, there's no way of avoiding it. You're going to have to integrate this guy as an integration by parts. So I'll do it over here. With respect to x. And I'm going to call UF, I'm going to call UG. And over here, we have F, which is this guy. Its derivative with respect to x is this guy. G is this guy, and its integral with respect to x is this guy with a 1 over y. There's all the pieces. So according to integration by parts, it's f dashed big G, take away the integral of f, sorry, it's just f big G, take away the integral of f dashed big G dx. So you're going to get xy of this guy, take away the derivative, which is y, times this guy, dx. A little tidying up, you get this guy. A little tidying up, you get this guy. And now, you integrate this guy with respect to x, you get e to the xy times another one of those guys. And don't worry about the plus c's, they get taken care of by the arbitrary constant. So it looks like we're going to have an x e to the xy minus a 1 over y e to the xy. Interesting. Plus a constant, which in this case will be an unknown function of y. And those guys cancel. So I'm really just left with this guy, plus an unknown constant. Okay, so put a little bubble around that to keep an eye on it so I know where it is when I need it. There we go. So let's move on to the second one, which is x squared e to the xy. And if we integrate that with respect to y, well, actually, you don't need anything too much. You're going to get an x squared e to the xy part, and then you're going to get a 1 over x. You know, e to the xy gets you e to the xy times a 1 over x, and that becomes x e to the xy, plus some unknown constant in terms of x's. I'll put a bubble around that one. And now we take this guy and we merge it to this guy, and we got really lucky because both pieces have the same piece. So there is our potential function. Now, the rest of that question, which I haven't actually told you about, is the information to do with the curve that's being used and its start and finish value. Well, the curve is given in terms of a space curve, and it's a cosine of t with 8 sine t, and it's going to start at 0 and it's going to finish at pi upon 2. So let's find the position at 0. That's the start. So it's going to be the cosine of 0, comma 8 sines of zeros, and that ends up being 1, 0. And then we'll do the guy at pi upon 2. So it ends up being the cosine of pi upon 2, which we know is 0, and 8 times the sine of pi upon 2, which we know is 1. So you're going to get a 0, 1 times 8, 8. So I know the start and the start coordinates. I know that's its position vector, but position vector is just another way of telling you in a coordinate, in a vector form, the coordinates of something. So there's the coordinates of the end. So to get the line integral, I just find the integral of c f dr. And the fundamental theorem of line integrals says it's the coordinates, or it's the value of the function at the end, so its coordinates are 0, 8. Take away the guy at the start. And what do we have? Well, we have 0 e to the 0 times 8. Take away 1 times e to the power of 0 times 1. That ends up being 0. And that guy ends up being e to the 0, which is 1. So you end up with -1. And that's actually the correct answer. There you go. So from, if you did, and you do have to do all the in-between parts, but from start to finish, there's really a number of steps that are quite common. First one is prove that it is a conservative field, because you know the first question that you don't check it and you do all this work and then it doesn't work is the question you should check. So we'll assume it goes by the first hurdle. We've done that check. We then have to find the potential function using this integrate two things and match them up. Check. And then blend the two answers together. And then you're going to be given, hopefully, some easy information where they just tell you the coordinates of start and finish, right? But they might give you a space curve or an x equals y squared or something, and you have to find the coordinates of the start and finish. But once you've got those guys, you're then left with your final step, which is this guy here, the fundamental theorem of line integrals, which says you evaluate the potential function, this guy, at the coordinates of the end, take away the value of the potential function at the end, and boom. End, take away start, and boom. There's your answer. So let's do one last one. So number 11 is going to be it. at least a version of number 11. The guy we've got is x to the 5, y to the 5. And we're given the coordinates of where you start, and we're also given the coordinates of where you finish, right? So there's the start, there's the end. Okay, so that's a lot cleaner. We have less things to do. Can you just assume here that it is a conservative field? It's dead easy, both guys are 0. So we'll pretend that we checked that. And now we're going to find the potential function by using the property that the gradient of the potential function is equal to the original vector field. And so this guy is going to be equal to that guy. Now we start by matching these two, we get this. And if we integrate it, we get 1/6 x to the 6 plus an arbitrary function, an arbitrary constant, which we consider to be some function of y because y is a constant. And then we do the other guy, who's him. And you get, oops, that's a 6. You get 1/6 y to the 6 and some arbitrary constant, which we consider to be a function of x. And then we blend them. Well, we need this guy and we need this guy, and these two guys allow us to do that. So basically, when you blend them, you get that. So there's our potential function. Now, since we know the start and finish coordinates, let's get the line integral over this. I think it was a straight line joining P to Q, or a curve joining P to Q, or who cares, because it won't really matter how you got from P to Q, because it's only the start and finish coordinates that actually matter for a line integral that comes from a conservative field, at least. So it's going to be the coordinates at the end, right, the value of the potential function at the end, times the value of the potential function at the beginning. Okay, if you plug in 3, God in Himmel, what a horrible number. Should have thought this out before I did it. 3 to the 6. Okay, so I'm going to write it down as 3 to the power of 6 over 6. Right. Take away, a much easier answer, 1/6. And if I had I can do it, I got a calculator around here. Here, I'll do it here. I've got an emulator. So 3 to the power of 6 is some huge, massive 729. Okay. Then divide that by 6, and you get 121.5. I don't like that. Let's make that a fraction. Okay, I get 243 over 2, take away a 6. Let's do that now. So take away 1/6 and make that a fraction. Oh, I'm not right. Okay. 1/6, check. 3/3, check. 1/0, check. That is a 6th. Yep, that's a 6th. This guy is 3 to the power of 6. Oh, yeah. Plus another 3 to the power of 6. That's what I forgot. Okay. And if you do 3 to the 6 plus 3 to the 6, take away 1/6, you will get 1457 over 6. Because that's what Webber tells me it is, and I believe it. And that is the end of 16.3, the fundamental theorem of line integrals. So hopefully, well, there's 11 questions in the homework. Hopefully I've given you enough help to go through that. And I'll see you all on Wednesday. So bye-bye for now.